Semiconductors and Transistors by Jonah Cowanese. Some electrons in solids are shared between atoms and move freely. In metals, a lattice of positive ions is surrounded by a sea of delocalized valence electrons, which are free to move between atoms. These electrons drift randomly with essentially no net movement. When an electric field is applied, they drift against it and are able to conduct electricity. In insulators, atoms are held in a lattice structure by strong covalently bonded valence electron pairs. These electrons are not free to move, and so cannot conduct electricity. Band structures and electrical resistance. For an insulator, all the valence electrons are used to form a covalent bond to hold its atoms together within the lattice. The valence band is full, therefore the valence electrons are locked in position and can't move. The valence band is separated from the conduction band via a very large forbidden energy gap. Therefore, at room temperature, the electrons don't have enough energy to jump the gap, so there are no electrons in the conduction band. Since the conduction band is empty, its resistance is infinite. For a conductor, the valence band and conduction band has merged, leaving no forbidden gap, hence the valence electrons for metal atoms are shared. The electrons gain high energy and are able to move freely and therefore able to conduct. As the temperature of a conductor increases, its conductivity decreases and its resistance increases. The conduction band has the most electrons out of all of them. For a semiconductor, only a small amount of energy is needed if they are going to jump the forbidden gap from the valence band to the conduction band. At room temperature, some electrons can gain enough thermal energy to jump the forbidden gap to the conduction band. As the temperature of a semiconductor increases, its conductivity increases and its resistance decreases. The semiconductors have very few electrons. The net absence of an electron in a full valence band is known as a positive hole. Holes act as a positive charge carriers and move in the direction of a conventional current. Positive current flow relies on the movement of holes from one atom to another. The hole is filled by a neighboring electron, which simultaneously leaves behind a new positive hole. As the electrons are attracted to the positive in the holes, the electrons are caused to move faster when subject to the holes. This therefore results in increased current and conductivity. Semiconductors can be classified into two categories. Firstly, intrinsic semiconductors, which are semiconductors that are pure. These semiconductors conduct electricity by electron-hole pair conduction and have moderate conductivity at room temperature. Secondly, extrinsic semiconductors, which are semiconductors that have other types of impurities added. The impurities added to the semiconductors can dramatically increase their conductivity by modifying the electrical properties. The doping of the semiconductor is the addition of a different external atom to the pure crystal lattice of the semiconductor. Doping assists the conduction of the semiconductor because there is an energy gap which allows for extra energy levels to be formed and fill this gap between the valence and conduction gap. This means that it is easier for these materials to conduct because the energy difference between the valence and conduction bands for such dopant atom is less. There are two different types of doping, p-types and n-types. Group 3 atoms have one less electron in valence shell than group 4. When added into a semiconducting lattice, the three valence electrons form covalent bonds with surrounding atoms. The absence of a fourth electron leaves a positive hole in the lattice which is able to act as a positive charge carrier in the valence band. This increases positive charge carrier density, increasing conductivity. The majority of charge carriers are positive, so it is called p-type. Group 5 atoms have one more valence electron than group 4 atoms. When added 4 of its 5 electrons from covalent bonds with adjacent atoms, one remains unbounded. This electron can be easily prompted to the conduction band and act as a free charge carrier, increasing negative charge carrier density. This increases conductivity and reduces resistance. The majority of charge carriers in semiconductors doped with a group 5 elements are negative, thus these semiconductors are n-type. Thermionic devices have many disadvantages that can be overcome with solid-state devices. For example, thermionic devices, triodes, are made of an evacuated glass tube with a cathode heated by a filament and a charged metal grid to amplify the electrons sent by the cathode. However, the glass was very prone to breaking, as well as losing its vacuum properties over time. It needed a high voltage requirement, and some of the energy was lost in heat energy and therefore inefficient. Thermionic devices are very large, heavy, and fragile, and unacceptable for the demand for smaller and more efficient communication, especially during World War II. Solid-state devices, on the other hand, could be constructed on a single silicon chip and were very cheap to construct. Unlike thermionic devices, they did not need to heat up before working and cool down afterwards. They had a much greater speed of operation and could be easily used in portrayable, smaller and tougher devices.
Created using Powtoon.